Yeah, thank you very much to the organizers for inviting me to this great conference. So what I'll do is I'll dedicate most of the talk to talk about some new ideas we have for understanding the nonlinear Hall effect in time reversal invariant materials. But having so many great experimentalists in the audience, I could not avoid the temptation of talking about some other stuff. So these are going to be basically very quick elevator pitch type of talks about some new proposals that we have for detecting certain kind of spin liquid states. And also a proposal to detect a conventional type of a collective mode in strongly interacting metals. Yeah, so this is a one-slide summary of the main ideas I want to convey in this first part of the talk, and the part that is related to the nonlinear Hall effect. So I want to convince you that in metals that lack inversion symmetry, there is a correction to Newton's law, according to which the acceleration of the electron liquid scales not with the linear applied force, but instead with the square of the applied force or applied electric field. And this correction to Newton's law, this acceleration is always orthogonal to the applied electric field, so it's a kind of Hall acceleration, and it's controlled by the Berry curvature dipole, which is defined as the gradient of the Berry curvature with respect to momentum over the occupied states. And I'll show you how this nonlinear Hall acceleration is behind the nonlinear Hall effect that can be present in time reversal invariant materials. And then I'll present to you a remarkable sum rule that we found for the rectification conductivity of time reversal invariant materials. So basically, if you take the rectification conductivity of time reversal invariant materials and you integrate it over frequency, you will get a quantity that depends only on the Berry connection of the bands. It's completely independent of band energies. This is why we call it quantum geometric sum rule. So this net rectification spectral weight, if you wish, is a purely quantum geometric quantity for time reversal invariant materials. So let me begin by reminding you about the notion of Drude weight. So the Drude weight is one of the central notions in our understanding of metals. It basically tries to answer the question of what happens to Newton's second law for a metal. So if you were in the ideal clean limit, the electrons will accelerate under applied electric field, and the Drude weight will measure basically the inverse inertia of the liquid. What happens in realistic systems is that the electrons eventually saturate into some terminal velocity. And that terminal velocity is basically what determines the conductivity. But the importance of the Drude weight, in a sense, is that it measures this intrinsic inertia of the electron liquid. The conductivity always has intertwined the information of the friction that the electrons are experiencing with their inertia. So the Drude weight is, in a sense, a more fundamental notion when you're thinking about a fluid, because it's measuring its inertia. The friction will depend on, how clean is the substrate, and so on, how clean is the material, so it's extrinsic. But more practically, basically what you will do to compute this inertia of the electron liquid is to integrate the Drude Hall. The integral, if there is a good separation between interband and intraband transitions, the integral of this Drude peak will measure basically the inverse inertia of the electron liquid. So let's consider a simple question that, actually I'm surprised that nobody had considered before. Let's try to compute the acceleration of electrons in a Bloch band, the acceleration operator. So for that, let me quickly remind you of how to construct the position operator projected into a Bloch band. So in vacuum, position is just the gradient with respect to momentum. In a crystal, you can show that the position operator is basically the gradient with respect to crystal momentum plus the Berry connection. And so this has a very important consequence, which is the projected position operator into a Bloch band is no longer commutative along different directions. And basically the Berry curvature is the quantity that measures this lack of commutativity of position operators. So this is a very nice way to think about Berry curvatures as an operator. It's some operator that is diagonal in crystal momentum and it's locally measuring how much the position operators projected into a band lack to commute. So once you know that representation of the position operator is basically a two-line exercise to derive this famous formula for the anomalous velocity. So take the Hamiltonian of a single Bloch band coupled to a uniform electric field. And so the velocity is just the derivative of the position with respect to time, which you can compute just by taking the commutator with the Hamiltonian, and you'll find two pieces. One is this group velocity, and the other comes because of this lack of commutativity of the projected position operators. So you'll get that the velocity operator has this extra anomalous piece, which is proportional to the cross product of the Berry curvature and the applied force. So then, let's go one step further and consider the rate of change of the velocity operator. So it's basically also a very simple a couple of lines of math to take the commutator of this operator with this Hamiltonian, and you will arrive at the following expression for the acceleration. So the acceleration operator is made out of three pieces. The first piece is just Newton's law, so one part that gets with the applied force and the inverse mass, effective mass. There is another piece that is just basically the instantaneous rate of change of the anomalous velocity. So imagine that the electric field is changing in time, then the velocity will change in time. So that will give a contribution to the acceleration. But there is an extra piece that scales with the square of the electric field. And the coefficient controlling the proportionality of this bilinear of electric acceleration is the gradient of the Berry curvature with respect to momentum. So it's this Berry dipole. So the Berry dipole measures a kind of nonlinear acceleration, a nonlinear Drude weight that metals can have when they have no inversion symmetry. So how to get the nonlinear Hall effect from these ideas very quickly? So you could do Boltzmann transport to get the nonlinear Hall effect very, very, very quickly. So basically, in the steady state, when there is scattering, the distribution function will settle into some new distribution function that is just basically the displaced distribution function controlled by the scattering rate. So if you just do a Taylor series of this expression and gather the second order terms, you will find two terms. So one is a purely semi-classical term, does not require Berry curvatures. But you will also get an additional term that is proportional to this gradient of the Berry curvature of the occupied states, but it's also proportional to the scattering rate. So this is how we understood this effect a few years ago with Yang. But so basically what I'm trying to say now is that maybe a deeper way or a better way to conceptualize this is that here when you're computing the current, you're seeing basically the terminal velocity of electron flow. So this calculation of the nonlinear conductivity is contaminated, quote unquote, from the information of the scattering rate, of the friction that the electrons are experiencing. So a better way to think of it is this very curvature dipole is as a type of nonlinear Drude-Wave, something that measures an acceleration, as I introduced first. So, but let's see what are the essential properties of this very curvature dipole. So there is basically two conditions that you need to satisfy for this very dipole to be non-zero. First, the material needs to break inversion symmetry. You know, any second order response coefficient in the electric field will vanish if you have inversion symmetry. But the material needs to also be a metal. So it's clear because it's an average over occupied states of a gradient. So at zero temperature, you know, because of periodicity of the Brillouin zone, this will vanish for a completely occupied band. So, you know, and that makes sense. As I just said at the beginning, it's measuring a metallic property. It's measuring an acceleration. Insulators are not supposed to accelerate. So just like the Drude-Wave, it vanishes for insulators. But the important point is that it's non-zero for metals that break inversion symmetry. So in a sense, it is a form of order parameter for broken inversion symmetry in metals. And, you know, importantly, the Berry curvature is odd under time reversal, but the gradient of the Berry curvature is even under time reversal. So this average can be non-zero even in a time reversal invariant system. So the general conditions for it to be non-zero is that you need to have a metal that breaks inversion. So for example, in 2D, you might imagine if you have some Fermi surface that is, you know, cut by a mirror plane, then the Berry curvature will be forced to change sign. And then in 2D, for example, you can think of this Berry dipole as a vector that points along this gradient of the Berry curvature. Okay, that's kind of the essence of the effect. So the effect was recently experimentally discovered by two groups following some initial first principle calculations by Binghai. So King Fai and Pablo Jarillo Herrero basically independently, simultaneously discovered the effect. King Fai will tell you more about the experiment, so I won't tell you much more about this. Right, so what I just showed you is basically sort of the simplest kind of single band picture for how to think about this effect. So what we did in this more recent paper was to develop a very general second order theory of transport and optical effects in any band structure. So this we basically sort of, you know, took the approach of some earlier pioneering works of using this gauge that makes the calculations much easier, and we added just one small ingredient to the perturbation theory, which is we did perturbation theory with an explicit relaxation rate. And this has the advantage that basically we can, you know, the complication of perturbation theory is more or less the same as in clean perturbation theory, but it has the advantage that you can take DC limits, AC limits safely. There is no issue. So we have a complete formula that captures, I claim, all second order optical transport effects in any system, metal, insulators, and as long as you can, you know, model the relaxation processes by relaxation time approximation, they should be in this formula. Okay, so, and with that formula of the very general second order conductivity, we found this SAM rule. So let me state the conditions for this SAM rule. So basically it's a SAM rule that is about the rectification conductivity to linearly polarized light. So that conductivity is measured by the real part of this second order conductivity tensor with opposite frequencies, so that you get DC current. So the statement is, if you integrate the real part of that tensor, you get a quantity that has no knowledge about band structure, band energies, let's say, only about the Berry curvatures and the Berry connections of the bands. Here, A bar is the off-diagonal Berry, non-abelian Berry connection, and the A is just the usual Berry connection. So it's quite remarkable sum rule. It knows nothing about, the only condition is time reversal symmetry. So the material needs to be time reversal symmetric, and it's strictly true in the clean limit. Okay? So let me explain where the terms come from. So this first term here is the Berry curvature dipole. This term comes from intraband processes. So this is the spectral weight of a very sharp through the light peak, which is related to this nonlinear acceleration near zero frequency. So again, it's like a through the weight. And these other terms all come from interband processes. So processes above the interband optical threshold. But they are also purely quantum geometric. So where to study this? Bile semimetals, as many previous speakers have emphasized, are natural platforms to understand nonlinear optical phenomena. So also in 3D, the sum rule is very interesting because the right-hand side, has is cubic in the Berry connection. So in 3 dimensions, it's dimensionless, like the theta angle in topological insulators. So in 3D, there's quite nice properties. The trace of this Berry curvature dipole tensor is also quantized in fundamental units in 3D. So here, with our formalism, we can, for example, describe the crossover from the quantized circular photogalvanic effect of Fernando and Adolfo and collaborators down to the low energy peak of the Berry dipole. So we have basically a theory that can describe all these interband and intraband processes on equal footing. And so the idea is that this spectral weight of the real part of that rectification conductivity will measure this nonlinear through the weight of Bile semimetals. Okay. Another an interesting platform within this Bile semimetal type of materials is this bismuth tellurium iodine. This is a trivial insulator that can be driven into a TI with pressure. And we have done some recent first principle calculations that show that this Berry dipole is largely enhanced near that transition. So just by measuring transport, this nonlinear transport, you can basically observe the features of this topological trivial to TI transition. Yeah, so that's basically the summary of this first part. So metals without inversion symmetry have an anomalous acceleration that is controlled by the Berry curvature dipole, which is a gradient of the Berry curvature over momentum space, an average of that gradient, and it gives rise to this nonlinear Hall effect that is allowed in time reversal invariant materials. And also there is a remarkable sum rule for the rectification conductivity that characterizes rectification to linearly polarized light in time reversal invariant material. How much time do we have?
Just 5 minutes.
5 minutes. Yeah, so with that, basically, I close that first part, and let me kind of give you very quick elevator pitches of these other ideas. So this idea is a proposal for a smoking gun type experiment to detect some type of spin liquids, the so-called spin liquids, the U1 spin liquids with gapless spin-offs. So basically the idea is that these states are insulators for DC transport, so the real part of the conductivity goes to 0, but they are not completely dead insulators. So if you apply magnetic fields to them, and shine light, you can see an analog of the cyclotron resonance in these materials. But there is a characteristic difference with respect to ordinary metals, which is that they lack the Kohn mode. This is closely related to the fact that they are strongly coupled to a U1 gauge field. So in metals, typically the cone mode would be the strongest harmonic of the cyclotron resonance. So they'll display all the higher harmonics, but they will lack the cone mode. The key challenge to observe this is that the residue of these higher harmonic peaks of cyclotron resonance will die as the materials become more and more insulated. So this is some proposal that would work for spin liquid candidates that are not too far from the mode metal insulator transition. In principle, they are always there, but the residue of the peaks will just become vanishingly small as you go, as the material becomes more and more insulated in this fashion. It's 1 over mod gap to the 4th power, basically. So, the spin-on Fermi surface is a very interesting state. It's basically a state in which the electron breaks into a neutral fermion with an emergent photon coupled to some boson that carries no spin, but carries the charge. The boson is gapped, and these spin-ons are left at low energies to form, a gapless Fermi surface state, basically. This state is believed, from the point of view of models, is believed to exist. That there is some arguments and numerical evidence that it might exist near the metal to insulator transition in the triangular Howard model. Okay? There is several candidate materials that are consistent with this spin liquid hypothesis. Tantalum disulfide. There is the organics, the MIT in particular. We also propose that maybe these mixed valence insulators might have a state that is closely related to spin-on Fermi surface. So there is a few materials that are good candidates.
Here, this tantalum disulfide, you mean it's a spin polarized? Or?
So, it orders into some charge density wave, but is left with 1 electron per unit cell. And there is no evidence of ordering of the spin of that electron.
I see.
So people have argued that it might be a spin liquid. So, the reason why they display cyclotron resonance is very simple. All you need to get cyclotron resonance is basically a mechanism for the spin-ons to form Landau levels, and then to have a matrix element of coupling to light, so that when there is resonant absorption, you will, when the light frequency matches the Landau level spacing, you will get resonant absorption. And so basically the idea, if anybody's interested, I can discuss this in more detail, is, the physical photon is coupled to the chargon, which is making a mode insulator, is gapped, but the chargon is coupled to the spin-on via this emergent photon. So when you apply a physical magnetic field, the chargons sort of, respond like an insulator, so they develop diamagnetism. So they self-consistently produce an emergent gauge field for this photon. So the spin-ons C. So the spin-ons will have Landau levels in physical magnetic field. And so it was pointed out some time ago also that in the absence of magnetic field, this state has a power law optical absorption. It's not a dead insulator, so it absorbs light at a very low frequency. So the idea we're proposing basically is that, combine magnetic field with that, you will see cyclotron peaks. But there is basically the cone mode is absent. And the idea to understand why it's absent is simple. So the cone mode, basically, this is a cartoon of the Fermi surface. So the cone mode is the mode that appears from the L=1 displacements of the Fermi surface, from the global displacements of the Fermi surface in the presence of a magnetic field. But those are frozen because of the coupling to the gauge field. But these higher harmonic deformations of a Fermi surface, like this dematic deformation of a Fermi surface, remain soft. This is the one that, this deformation of the Fermi surface is the one that gives rise to the second harmonic and so on. So this is why they have no cone mode, but they have higher harmonic modes. And here is some numbers more specific. You can plug the expected width that you will get from gauge field fluctuations for these peaks, and the width is still smaller compared to the peak energy, so they are in principle visible, but the key challenge, as I mentioned, is that the strength of the peaks will go down as the material becomes more insulated. And so very quickly, also just to give you the elevator pitch of this other idea. So we have found, we're proposing the appearance of some new collective mode in correlated metals. So metals typically have just a single collective mode outside of the particle Hall continuum. Is this so-called plasma mode. But it's possible when you have strongly interacting Fermi liquids that they actually develop an extra collective mode. This extra collective mode is a little bit like the shear sound, the transverse waves of a solid, even though the system is still a liquid. So we have done some detailed calculations of the conductance of narrow channels, of clean narrow channels, in which, clean meaning the width smaller than mean free path. And so this is a plot of that conductance. So the blue line is for the Fermi liquid that has the mode outside the particle Hall continuum. The blue line is the one that has the modes, a Fermi liquid that has the mode outside of the particle Hall continuum. And the orange is a Fermi liquid that would have the mode inside the particle Hall continuum. So they have some cusps before the mode exits the continuum at the edge of the particle Hall continuum, but these strongly interacting Fermi liquids that would have this shear sound mode will develop some resonant dips in the frequency dependence conductance controlled by the dispersion of this mode when you try to pass current through narrow channels. I can explain the intuition of that. It's actually very simple when you think about a crystal. What happens when a crystal and you are just pinning the boundaries, basically. So if you probe the electron liquid at the right frequencies, it responds like a crystal. It's kind of the bottom line, even though it's still a liquid. Yeah, so with that, let me thank you for your attention.
Questions?
Yes, summary result is really interesting. Get some idea on two-band models. This sum rule is related to the skewness of the polarization distribution, and this seems like your result seems clearly like very general. So I was wondering whether you can relate it to a physical property of the
Yeah. So I'm aware.
Yeah, I think
So you're mentioning. So the answer is no.
Okay.
I don't know how to connect it, but there's probably some connection.
Yeah, some
We
physical-
haven't just worked it out.
Mhm.
It's probably some general connection. Some rule that I mentioned here.
So if the spin on Fermi surface is, I take it the rock fermion and I guttural or projected, right? To get a spin on Fermi surface, I take a Dirac fermion charge and I guttural projected, right?
Why Dirac? No, it doesn't have to be Dirac. So in the single orbital Howard model in the triangular lattice, you just have one band, a field.
How do I think of these Landau levels starting from a guttural projected?
Yeah, so physically, basically what is happening is that when you apply magnetic field, there is some expectation for the spin chirality. Okay, so if you want to start from the insulating side, from the Heisenberg type model of the insulator, in the magnetic field there will be some expectation value for the spin chirality. And the spinons, when they move, they see this spin chirality as a source of flux. It's one way to think about it from the very insulating limit. Near the mode transition, maybe what I sketch as a principle, it's basically the chargons, they are weakly gapped, right? They are making an insulator. So they are trying to respond to the applied magnetic field to screen it. Like, they are a diamagnetic insulator basically. So, but because of this, they are also self-consistent sources of this emerging gauge field.
If I start in the large magnetic field limit where I have Landau levels,
Oh,
and then
this is
Gassula
just
project.
for you to see that they see a Lorentz force. Okay, so it doesn't have to be large, right? So like cyclotron resonance, there will be conditions, right? So there will be some omega c tau type condition for these peaks to be sufficiently visible. But you don't have to go to the ultra quantum limit. Okay, it's like cyclotron resonance. But this is, why I think it's a good experimental proposal, because it's like cyclotron resonance. Cyclotron resonance in a metal, you don't have to go to ultra quantum limit to see.
But for cyclotron resonance, you have to send in a microwave to the excitation. So
Yeah.
the microwave couples to the.
Yeah, so that's the idea. They have some kind of Landau levels, they have some kind of Lorentz force. And they also have a dipole, some amount of dipole coupling to light. So they have
For spin-off.
absorption, yeah. They have at finite frequency, they have amount of coupling to light. This is why they have real part of conductivity that dies like a power law.
This is the electric dipole, not the magnetic dipole transition.
Yeah, this is electric dipole.
I mean, I guess if you have a Dirac fermion, right? So I think the story, I'm not remembering well, but the story was that you're gonna have to have a spin on Fermi surface because there's no way to kill the Berry phase even by Gassula projecting it.
I see.
So that guarantees.
No, maybe this is a story I'm not very familiar with.
I might
So you
be
should-
remembering it wrong, but I think that was the story. So now if I apply magnetic field and then Gassula project, how do I see? Because Gassula projection.
The spinon,
Strongest.
the spinon in terms of microscopic wave functions is very poorly understood. So you're asking me a very tough question. But yeah, the physics is more or less like what I described by the microscopic wave function.
Did you try the sum rule for the circular effect? Did you try integrating in frequency and see what happens, at least the low
We did
frequency?
try to see something for circular, but we couldn't get anything particularly nice. So maybe just we didn't do, we're not clever enough for it. We did try.
Well, very simple question about the zero sum you mentioned.
Yep.
Well, I assume here is well, recently Shidai talked about the chiral zero mode, chiral zero sum from the YSM metal. But my question is even simple. Like in kinetic metal system, before experiment, this zero sound, what kind of system it was observed?
This shear sum.
The shear sound.
Yeah, so this mode was believed to be present in is believed to be present in helium-3. Yeah, this is very good for this question because this is something I did not emphasize. So the mode is believed to be outside of a particle Hall continuum even in helium-3. But when you plug the Landau parameters of helium-3, it's just barely outside. Okay? So in the 70s, there was an attempt to detect this mode experimentally that claimed that they saw evidence, but it was then countered by some other papers. So it was not too much, like 2 papers on this. But in helium, it might be there, it's just too close to the particle Hall continuum. But so what we're trying to emphasize is that this mode is present in metals, and it also remains linearly dispersing because it's a purely neutral current mode. And the criterion is very moderate, okay? So the quasi-particle mass, when you translate the criterion into how heavy the quasi-particles have to become for this to exit the continuum.
This was already observed in some metals?
No, it has not been observed. I know, so, but what I'm trying to say is, it might be hanging around in a lot of metals because it just requires moderate interactions, but it's just very hard to excite and couple to it. So we basically are trying to propose these narrow channels, and also it might be possible by turning on small magnetic fields, because when you turn on magnetic fields, this mixes longitudinal and transverse modes, so that gives a little bit of weight on the density for this mode. So this is the spectral weight of the density correlations, and this is the dispersion of the mode. So then you could do something like plasmonics. If you turn on a weak magnetic field near an edge, so you could do near field optics, the same kind of plasmonics that have been done to excite the plasmons in graphene.
Thanks. One more question? If not, thank Inti again. much.